All right, atomic theory. So atomic theory began in the 4th century BC with Democritus. He was the first one to suggest the existence of atoms. However, he probably couldn't develop it any further because people probably thought he was crazy for suggesting the existence of such a tiny particle that they could not see. In the early 1800s, John Dalton tried again, and he came up with an atomic theory to try to explain to people that these things did exist. His atomic theory says that all elements are composed of tiny indivisible particles called atoms, that atoms of the same element are identical, and atoms of one element are going to be different from those of any other element, meaning if you have 2 pieces of gold, the atoms in the gold are going to all look the same. But if you have a piece of silver and a piece of gold, those 2 particles, the silver atoms, are not going to look like the gold atoms. Atoms of different elements can chemically combine with one another in simple whole number ratios to form compounds. So we can take hydrogen elements, and we can take oxygen, and we can combine them in a 2-to-1 ratio to get water. So 2 hydrogens for every 1 oxygen is going to make us have water if we can combine them chemically. Chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element are never changed into atoms of another element. So you get a chemical reaction when you have 2 atoms that are connected, and you break their bond, and you are rearranging them. So like you're moving their seats. You can't, however, take a gold atom and turn it into a silver atom. You can change what the gold is connected to, but you can't change what it is. And for the most part, all of these things are still accepted to this day. The only one that science has proven incorrect is the first one. And we know that those particles are divisible. That's how we get our new elements. We're shooting protons at one another, forcing them together. So we know that there is more to this atom than just those pieces, and that we can separate them, recombine them, things like that. Those subatomic particles are the protons, neutrons, and electrons. And some of these can be broken down even further into quarks, but we're not going to go that far. So the protons are a lowercase p with a plus superscript. That's its symbol. And that's because it has a +1 charge. It has a mass of 1.67 times 10 to the negative 24th of a gram. Next are neutrons. Neutrons are a lowercase n with a superscript 0. And that's because neutrons are neutral. They carry no charge. Their mass is also 1.67 times 10 to the negative 24th of a gram. Neutrons and protons are located in the nucleus, and they have a much larger mass than our third particle. These guys make up the bulk of the mass of an atom. Our last particle are the electrons. They are a lowercase e with a negative sign, and that's because they have a -1 charge. And electrons are quite a bit smaller than our other 2 particles. They have a mass of 9.11 times 10 to the negative 28th of a gram. So the electron's mass is negligible in this case. We are not going to count it in the mass of an atom because it is such a small part of the atom, even though it plays a big part on how the atom behaves. So there are 3 scientists that we're going to talk about that got us to where we are today with how we know about the size of these particles and their charges. First is J.J. Thomson, and J.J. Thomson actually discovered electrons with his cathode ray experiment. So this is a cathode ray. It's a tube. It's very similar to the tubes in the back of older model televisions. You have a negative plate, the cathode, and then you have a positive plate, which is the anode, and in the anode is a slit. There is a current running between these two plates. When that current runs, particles come from the cathode to the anode. There's a fluorescent screen at the end of the tube, so J.J. Thomson could see where the particles were landing. He also had a magnet that went on the top and the bottom. It was also hooked up to an electrical charge, so he could switch the polarity of the magnets. And when he turned the magnet on, he noticed that this beam was attracted to the positively charged plate on the magnet, and it was repelled from the negatively charged plate. So when he switched the current, he noticed it would bend the other way, again being attracted to the positive plate and deflected from the negative plate. So he was able to determine that there is some other particle in these atoms that carries this negative charge, and so he gave it the term electrons. Then came Ernest Rutherford, and Ernest Rutherford was actually a student of J.J. Thomson's, and he tested the theory that electrons were evenly distributed throughout the atom. So initially they thought that there were protons and electrons mixed in the nucleus. And what he found out was this was not the case. He has this alpha particle, which has a positive charge, alpha particle emitter, and he has his fluorescent screen here so he can see where the particles are landing. There's a slit there so that the alpha particles can get into the screen. And he put a very thin piece of gold foil in this screen. So when he turns the alpha particle emitter on, he notices that most of these particles go straight through the gold foil. He probably assumed that they were going to be deflected back towards him. But he found that most of them went straight through. Some of them, however, were deflected. This gave him enough information that he was able to determine that the electrons were not actually distributed throughout the atom, but they were probably on the outside. The reason that these were deflected was because the nucleus of the atom has a positive charge. You're shooting a positive charge at a positive charge, it's going to repel and push it away. So he was able to determine that atoms are mostly empty space. You have this very, very tiny nucleus with its positive charge, and then taking up most of the room on the outside are the negatively charged electrons. Robert Millikan was the one who was able to determine how much of a charge was on an electron with his oil drop experiment. And so he has this setup. It's a chamber. Again, we have charged plates. We're using an electrical current to manipulate our particles. He has this atomizer, which turns this oil into a superfine particle. There's a slit in the top plate. And as these superfine particles of oil fall through the slit, he's able to watch them with his microscope. He turns the charged plate on, and as he changes the amount of electrical current running through the plates, he notices that the particles slow down, stop, and some of them actually reverse. So based on the distance that these particles of oil fell, the rate which they were falling, he was able to figure out that the charge on an electron is approximately -1.